Welcome to Lesson 3.9, Introducing Cryptography. In your Candidate Information Bulletin, we are in the Security Engineering domain. We are in Key Area of Knowledge I, which is to apply cryptography. Our topics in this lesson will include a brief history of cryptography, modern cryptographic services, cryptographic functions, algorithms and keys, key space, and strength of a crypto system. This is the first of 7 lessons related to cryptography. This is one of the most difficult topics for CISSP candidates, so we're going to go through it slowly in chunks to make sure that you have a really good understanding. Don't hesitate to go through a lesson again if you didn't feel you got all the concepts. At some point in this, you may feel like you are falling into an abyss, but I promise you, we'll pull you out. By the end of these 7 lessons, you will have a lot of confidence in your knowledge and skills related to cryptography. So cryptography is the science of secret writing that enables an entity to store and to transmit data in a form that is only available to the intended recipient. So our goal here is that I can transmit, or you can transmit, a message. It can go to an intended recipient, and nobody else, the carrier, however it got there, whoever else might be at the location, has any ability to read or understand that message unless they are the intended recipient. Now, cryptography is not new. We think of it as crypto systems as being part of the modern age and modern technology, but cryptography goes back way through the ages. We have what's called the manual era of cryptography, even before 1900 BCE, where they first appeared in hieroglyphics in Egypt. And then around 49 BCE, we have what's called the Caesar cipher. And we're going to actually look at the Caesar cipher because that's a foundation of one of our modern cryptographic concepts. And then we're going to move up thousands of years into the mechanical era. And in 1459, there was a creation of a cipher disk. So we stopped handwriting our ciphers, and we had a more of a mechanical way to create these. And in 1933, we had the very famous Nazi Enigma machine, which were used to transmit secret messages. When we move into the modern era, crypto systems use the power of modern computers. They're very powerful, but there is really this ongoing cat and mouse game because as computers get more powerful, the crypto systems that we have weaken because the computers have more power to potentially crack those crypto systems. And lastly, we have emerging technology of quantum cryptography. So if that's of interest to you, you may want to study that, but quantum cryptography will not be on your examination. We're going to start with taking a look at modern crypto system services. A crypto system is the hardware or software implementation that includes all of the necessary components. The crypto system can provide the following services. It can provide confidentiality, integrity, authentication, and non-repudiation. Confidentiality renders the data unreadable except by authorized parties. Integrity ensures that the data has not been modified. Authentication verifies the identity of the system, and non-repudiation ensures that the sender cannot deny that they sent data. So confidentiality, integrity, authentication, non-repudiation. Now you'll notice what's missing here is availability. Our modern crypto systems do not provide availability. So the cryptographic functions we're going to be looking at, there are 3 primary functions. Data can be encrypted, which provides for confidentiality. Data can be hashed, which provides for integrity. And data can be digitally signed, which provides authentication and non-repudiation. We're going to be studying, in each of the subsequent lessons, encryption, hashing, and digitally signing, or digital signatures, in order to provide confidentiality, integrity, authentication, and non-repudiation. So let's start with a conceptual cryptographic process. A cipher is a technique or a set of rules that will transform clear text, what we're known as plain text, what you currently see on your screen, into an unreadable form. And that unreadable form is called ciphertext or called a cryptogram. So we're going to take plain text and we're going to make it unreadable. That unreadable form will be called ciphertext or a cryptogram. And then we have to transform it back to clear text so our intended recipient can read it. So here's what the process looks conceptually. We start with our clear text or plain text. We apply a cipher. Remember, that was a technique or a set of rules that will transform the clear text, that plain text, into an unreadable form. and the output there is ciphertext or a cryptogram. Now we are going to send that or transmit that to the intended recipient. In its transmission, or even while it's sitting in storage, it is not accessible to anyone else other than the intended recipient, because the intended recipient will have the knowledge to how to unlock it or how to transform it back into clear text. So at the intended recipient end, we have the ciphertext. They're going to apply a cipher. It's going to be that same technique or set of rules that we use to turn the plain text into ciphertext. We'll use to turn the ciphertext back to plain text. And now they will have the clear text or plain text. So we go clear text, apply the cipher, ciphertext. Then we reverse the process, ciphertext, cipher, back to clear text. So to do so, we have some very important components known as algorithms and keys. An algorithm is a complex mathematical set of rules that are used in cryptographic functions. An algorithm is just another name for a modern cipher, but it's a complex set of mathematical rules. Now, there's nothing secret about the algorithm. Algorithms are generally publicly known. Now, there are some algorithms that may not be publicly known, used by national security agencies around the globe, but the ones that we use for commercial purposes are generally known. So the secret is not the algorithm. Everybody knows what the algorithm is. So something's got to be secret, and the secret is going to be the key. So a key, which is also known as a crypto variable, is a value that's used with an algorithm. And what the key does is it dictates what part of the algorithm will be used. So remember, this very complex mathematical set of rules. So we're saying what part of those mathematical set of rules are going to be used, in what order, and with what values or what variables. That's what the key holds. So the key has to be secret, because that's the secret part. Remember, the algorithms are publicly well known, but it's the key that really makes the difference here. That key dictates three things: what parts of the algorithm will be used, in what order, and with what values or variables. Key space is the possible number of key combinations. For an 8-bit key, so that's a key that has 8 bits, the key space is 2 to the 8th, or 256 possible keys. Well, if I'm an attacker, it's going to take me no time at all to try all 256 possible keys, and eventually I'm going to be able to figure out how the algorithm is actually working. So an 8-bit key certainly isn't going to suffice. 256-bit key, however, the key space is 1 to the 256th, or 1.1578 times 10 to the 77th possible keys. That's an expansive key space, and it would take an extraordinarily long time for an attacker to figure out, if they even could, what the possible key combination is. Longer keys are harder to break, but they do require more processing power when we're using them in an algorithm. So the strength of a crypto system is going to be the combination of the algorithm, the algorithmic process, the length of the key, and the secrecy of the key. Again, so it's going to be a combination of the algorithm. It's got to be a good algorithm that's been written. It has to have the algorithmic process. How do we actually use it? The length of the key, because that gives us how many different key space choices there are. And then certainly the secrecy of the key. If we chose a very long key in our cryptographic system, and then we exposed the key to an attacker, or we didn't properly secure it, and they were able to exfiltrate the key, well then all of the rest of it doesn't matter. The algorithm, the algorithmic process, or even the length, if we're not securing the key. So the primary thing we always need to be doing is secure the key. If one element is weak, the entire crypto system can potentially be compromised. And the work factor is the estimate of time and effort it would take for an attacker to penetrate or break a crypto system. So when you hear the term work factor, we're saying, how much time would it take? How much effort would it take? When we say effort, we're really talking about processing power. Would it take for an attacker to penetrate or to break a crypto system? Now, obviously, if we're exposing the key, it takes no time at all. The longer the key, the greater the work factor, and the more processing power that's required. But that same holds true, that the longer the key, the more processing power it takes to utilize that key and algorithm. So we've looked at some basic concepts. Let's do a lesson review. We started with an overview of cryptography, which is just the art and science, if you will, of secret writing. talked about modern cryptographic services and what they're going to provide in terms of confidentiality, integrity, authentication, and non-repudiation. We looked at our cryptographic functions, a brief introduction to encrypting and hashing and using digital signatures. We also did a conceptual understanding of how that's going to work. We talked about what an algorithm is. It's just a modern cipher. It's a complex mathematical function. We talked about a key. A key is just a value that we use that tells the algorithm three things: what part of the algorithm to use, in what order, and with what values or variables. We looked at the key space, which is a possible combination of keys. We discussed the strength of the crypto system and the related work factor. So these are just some basic concepts that you need to understand so that we can continue to discuss the entire realm of cryptography. So let's do a lesson 3.9, match the meaning. Cryptography, authentication, non-repudiation, a cipher, ciphertext, an algorithm, a key, and a key space. So take a few minutes, put me on pause, match the meanings, come on back, and we'll do them together. Cryptography is a science of secret writing. The goal is that I should be able to jumble up the words so they're in an unreadable format and that only the intended recipient can understand what I'm actually sending them. Authentication proves identity. Non-repudiation proves the sender. Non-repudiation means that the sender cannot deny that they sent the message. A cipher is just a cryptographic set of rules or techniques. Ciphertext is when we transform plain text to unreadable form. An algorithm is a complex mathematical cipher. Remember, a cipher was just a set of rules and techniques. Key is a crypto variable, that's the other term that you'll see used for a key, that we use with an algorithm. And key space is the possible number of key combinations. It's very important that you get all these down cold. So as we're going through these lessons, if you don't feel comfortable, feel free to go back through the lesson again. Our 3 CISSP exam tips for this lesson: that a crypto system is the implementation of cryptography, that the work factor, that's a term you're going to see probably in your exam as work factor, is an estimated of time and effort that it would take an attacker to break a crypto system, and that longer keys are harder to break, but they do require more processing power. Thanks for joining me for this lesson, and I look forward to seeing you in the next.